So welcome to the demonstration portion of our presentation. And usually when you get to into Space Studio and interior design, the steps you would take are either to open a new project and then import your design files, your C, C++, System C into the tool, or a pre-existing project, you can open that and browse to it, which is what we have done previously. So a previously opened project is what we have here for Motion JPEG, and what you're seeing here right now is an architectural design in our SimTech editor with all of the user IP running as software on an ARM Cortex-A9 dual-core. But before we got to this point, what I'd like to show you is to take a step back to our Elix functional specification or algorithm editor. We'll save that, what was there before, and just to show you what the algorithmic design looks like. And so here in Elix, what you want to do is that you want to run behavioral simulations of your algorithm, your functional specification, and make sure that it's working properly. You can make modifications to the code on the text editor here in the upper right, and basically run these simulations and look at the waveforms and make sure that it's running properly before you map it into an architectural implementation, as we saw earlier with the SimTech editor. So I'm going to reopen the design that you saw a few moments ago, and that's an ARM-based design with all of the user IP running as software right now, along with an operating system, in this case the Micro C2. And we've already made a run of the simulation, so we do actually have monitoring results, basically a data log of all the transactions that took place during the simulation. And so by opening the Space Monitor tool, we will pull in this data log of transactions, and then we're ready to generate a number of charts and graphs. So the highest level charts and graphs that we'll look at here would be first in terms of bus traffic. We see that we have 11% utilization of the bus, so there's no issue of congestion impacting the performance. But then we look at the two CPUs, because this is an ARM Cortex-A9 dual-core, and we see that one CPU is very heavily loaded, another is only moderately loaded. Okay. So here we have the inverse quantization, the inverse discrete cosine transform, and demultiplexing happening on the first CPU, core 0. But we also notice that it's spending just over a quarter of the time idle, which means that the iQuant and the IDCT and the DMUX are not getting enough data to do more work and to reduce the amount of idle. Now, the rest of the design, the rest of the user algorithm or design is running on the second CPU. And what we notice here is that we have two very, how shall we put it, very heavy functions running one at a time, switching off on this one single CPU. So this is our potential bottleneck. And so our alternatives as system architects would be we could add more CPUs and reallocate the software tasks, or since we have hardware as well as software options, why don't we do hardware acceleration on one or two of these functions? And so maybe what we'll do is that in the validator, which contains the Huffman decoder, why don't we take that and retarget it for hardware? Now in Space Studio, the retargeting of functions to hardware or software, you can use the same model. You don't have to run out and find different models for the software executable versus the hardware implementation, as you would do with traditional C and traditional Verilog VHDL. And so that retargeting in our tool is reflected by a drag and drop mechanism where I can select the validator containing the Huffman decoding here, currently under one of the CPUs, then drag it and drop it onto the AXI channel or bus, and voila. Suddenly our design topology changes. Our Huffman decoder is now sitting here as a hardware block. And that's also reflected in the design tree that we have here in the upper left window. We see now that the Huffman decoder is now outside. The little red letters say HW. The connectivity is to the AXI channel. Meanwhile, the CPU that it once resided on, only the line builder is sitting on that now. So there's one large, heavy application, the line builder running on the second CPU, while the first CPU, we leave that task assignment the same. Since the topology of the design has changed, what we'll have to do is we'll have to clean out the old files that were generated for the old topology, both hardware and software, since that's no longer valid. And then we regenerate the top level and all the different support files. And we again do that with monitoring. And I will also select to clear the file cache, just to make sure there are no other files sitting there. Now, this is a little bug that happens because of one of our tool chains being configured wrong, but that's not going to affect us here. It's actually for the synthesis. And so the first thing that happens during the generation process is that there's a communications analysis that's done on the design, and here and there FIFOs may be inserted to improve the communications between different modules. Also, other support files are generated, including things like linker scripts for software and the top-level topology for the hardware. Which in this case we now have the Huffman decoder block sitting at the hardware top level. Okay, so once all the files are generated, we then hit the build button, which calls the compilers. First, the ASCII System C compiler, which will compile the hardware portion of the design, and that's followed by the cross compiler that compiles functions to run as software executables on the ARM Cortex-A9. Okay, so that's done for our new configuration. And so we'll now run a second simulation. And what will happen is that we will paint 2 JPEG frames out of a motion JPEG stream that was recorded earlier, actually about a year ago. And this will take about 3 to 4 minutes. And this is usually the juncture where we pause to take questions from the audience. Another thing to notice is that here, if you see my pointer here, the binary files are being set up for the monitoring data logs to record all the transactions happening on components, on the channel, and on the CPU. And again, for the next 3-4 minutes, you'll see one and then a second image being painted on the VGA controller display model, that little blue window there. And this is where we can have the audience ask questions while the painting is being done. So actually, in this case, Jean-Jacques, if you have any questions about what you've seen so far, or what we were doing in the earlier configuration, we can do that now just to fill up the time. And let me know if you have your mute on. Okay, so we're about halfway through the first picture. So this is near the start of the motion JPEG stream with key at a distance on a block about it's about 300 meters south of our offices here in Old Montreal. So from somewhere around the starting point in the actual video file, Guy will walk to the left of the screen and then forward towards the camera, and that's the second frame that you'll see being displayed here. And again, during our previous presentations, this 3-4 minute block is usually where we have the customers ask us questions about things that they saw, about the models, etc. And let me just test this here. It may be possible if you click on the editor window, it'll throw the VGA to the back. And yes, okay, we can start like scrolling through models and showing people like the top level of the C++ file to show them the includes, the interface, which corresponds to System C, TLM2, and then inside the single thread for the task. So this is multitasking, but each task is a single thread, and inside this thread we'll have all the operations plus the communications that take place between different blocks. Like here, we read data from the inverse quantization, and then further down we write the processed data to the line builder. And if I hit on VGA again, okay, now we bring the VGA back up to the front, and we can look at the progress, and we see the second frame is being painted now. And the 3 to 4 minute pause that the frame painting gives us actually is one that usually we get like one long question and maybe 2 short questions. So the 3-4 minute pause actually is just about right. We sort of got lucky there. Now at DAC, what will probably happen is that we probably won't run the simulation interactively during live demos. We may just have it running in the background during idle time, just like at Embedded World, because what we're going to emphasize is a little more this time is what happens further downstream with the synthesis, and then those results will be downloaded to a Z board, and we'll have Z boards at DAC to show people the calculator example.
Okay.
Yeah. So before we were mostly emphasizing I think last year we had the rover controller, so we were showing the simulation on the floor at the ARM connected community pavilion, and then in the demo suite we would go into more detail on the rover, and then we would have the design already stored on a flash card to program the Z board. And we'll have that for the calculator too, but we'll show that we will be driving the Xilinx Vivado tools, and we can show net lists in between. And in the 2.5, we also launched Vivado HLS, the auto ESL synthesis tool. So after a meeting day, I will uninstall this and reinstall 2.5.0, and then also update my Xilinx installation, because I have 14.2, not 14.4. And there we go. So we've painted the second frame, and we see here in the bottom that the System C simulation has been stopped by the user. In other words, the System C stop command. So I will kill the VGA controller to stop the simulation, and then we can look at the results of our new architecture with the Huffman decoding retargeted for hardware to accelerate it. And were our instincts correct? Let's see, the AXI channel now has 12% traffic as opposed to 11. So again, it's not congestion, but this does reflect the additional data that's now moving back and forth between the tasks on the CPU, or CPUs actually, and the Huffman decoder block in hardware. Both CPUs seem to be pretty busy, and let's see what busy means. Is that good or bad? It's actually good. We're not getting any congestion because the idle time is still just under 8%. But note that this is like 1/3 of the idle time that we had before, which means that everybody else, all the active tasks, are actually doing more work now. And that's reflected by the large percentage of the total time taken up by the multiplexer, inverse DCT, and the inverse quantization. They're all doing more work because they're getting more data. When we look at the second CPU, you see that the line builder monopolizes it, so it's probably running as fast as it can under these circumstances. So as much data is being pumped into the line builder from the inverse DCT after getting information from the others, it's running just as fast as it can. And so that serves as an example of how we can do a slight architecture modification, and that has a tremendous impact on our performance. And so we'll stop the recording right here, Jean-Jacques.